Class? Okay, so we're going to move on to a new topic. We're going to talk about something called electric potential. And to start this out, let's say we have two charges, Q1 and Q2, and say they're separated by a distance r. And let's say Q1 is fixed, but we're going to move Q2. Let's say we move it away from Q1. So we'll say it starts at point A, and we're going to move it to point B. So we'll say it starts out, we'll call this distance here RA, and this distance here RB. And there's going to be energy involved. So it's kind of similar, like there's a gravitational force acting on this eraser, and if I lift it up, I'm applying a force through a distance, I'm doing work on it. And because gravity is a conservative force, then there's a potential energy function associated with gravity. And in electrostatics, these electrical forces are also conservative. And so we can talk about potential energy, just a change in potential energy as a result of moving this charge around. And so there's a bit of a problem though. Let's review potential energy. It's related to work. So a change in potential energy so let's say we have a displacement from A to B. And we define the potential energy to be equal to minus the work done during that displacement. So like here, if this is A, like the height above the ground, let's say, that'd be like HA, and I lift it up to height B, I'm lifting it up. So gravity is down, and I'm lifting it up. So the work that gravity is doing as this object is moving upwards, gravity is doing negative work. And that's why this minus sign is here, because we want to say that this eraser is gaining energy as it's being lifted. So if gravity is doing negative work, if we put that minus sign, that means we have a positive change in potential energy. And so it has more energy the higher it is, because if I release it, it's going to fall and gain kinetic energy. Where is that coming from? Okay, and again, potential energy can only be associated with conservative forces, but in electrostatics, we can define this potential energy function. Now, there is a problem here. Like when it comes to gravity, it's very easy to calculate the work. It's just the force times distance if we're lifting it straight up. It's not quite so easy calculating the work as we go from A to B. So I'm going to write this. The work as we go from A to B is approximately equal to the force times, let's call this displacement delta x. Now the reason I say this approximately equal to is because the force depends on the distance between the charges. I'm not liking this notation. I'm going to call this delta r. So we'll just say we're moving radially away from that charge. So delta r is a displacement, radially away from Q1. Q1 is fixed. And so the reason why this isn't approximately equal to thing, what is the force? Well, it depends on this distance separating them, but that's changing. Now, when it comes to the Earth, that's not really an issue because we're, thousands of miles away from the center of the Earth. So a change of a few meters or even a change of a few kilometers, the difference in force is going to be negligible. But here, we can have a significant change in force as we go from A to B. And this is one of those unfortunate situations where we need calculus to be able to do this. And so what I'm going to do is just write down the answer, which again, I don't like doing, but yeah, I'm going to have to just write it down. So the work along this path from A to B, so let me think. Kind of looks a little strange. If you have had calculus, this is a fairly easy thing. You put an integral sign here, and you turn this delta r into a dr, and you'd integrate from, say, RA to RB. So if you have had calculus, this is kind of a trivial thing to do. But if you haven't, then completely ignore what I just said. So I'll replace that with a delta r again. Okay. So this is the change, this is the work done. And remember, work is the change in potential energy. So what we have, delta U, would be the potential energy at B minus, change as we go from the final value minus the initial value. So delta U would be the potential at B minus the potential at A. And that's equal to minus the work. So if we write UB minus UA, that would be minus the work, so that would be a positive KE Q1 Q2 over RB minus KE Q1 Q2 over RA. So again, this result comes from calculus and our basic definition of work. So you kind of just have to trust that trust this result in an algebra-based class. Now, what we're talking about here is changes in potential energy. So it would be nice if we could just say the potential energy at this point is equal to this value instead of talking about changes. And again, that's what we did with gravity. Where we looked at, in order to find the potential energy function, we had to, say this is ground level, and then we could say like h equals 0 here, and then just calculate the work as we raise it up to some height h, and we can just pick this ground level to be 0. The problem is that we cannot do this with the electrostatic case, because we can't just set like r equal to 0, because then we're dividing by 0. And really, there's nothing we can plug in for r that's going to make something 0 naturally occur. And so what we do is we define what's called a point at infinity. We say, theoretically, electric forces do not have any limits on range. Theoretically, a proton in this marker is interacting with a proton somewhere in the Andromeda galaxy. Doesn't matter if they're separated by, 100 million light years or something. Theoretically, they still exert forces on each other. So it just depends on, r squared. So they'll get very small fairly quickly. But for practical purposes, once these charges become separated by enough distance, we can essentially say that one of these terms would just be 0. So what we do is we define a potential energy function where we say the potential energy, if r was infinitely far away. If we set r to be infinite, or just very large, this term is 0, then we say there's no potential energy interacting between these two charges because they're so far away. So we can define a potential energy for this distribution of charges just as a function of r, where our 0 level is defined when the two charges are infinitely far away. Okay. So again, no way to get around using calculus here, so you just have to kind of trust going from here to here Just trust me on that. If you don't trust me, trust basically every textbook written. So, yeah. Now, the topic of this is electric potential. And it's kind of an unfortunate name because potential and potential energy are different things. And the relation between potential energy and, like, electric potential energy and electric potential is kind of like the difference between electric forces and electric fields. So what we're going to do is we're going to say, like, the potential energy of charge 2 due to the electric field of charge 1, and it's given by this, we can say that this is Q2. We can just kind of separate these terms. So we have Q2 times KE Q1 over R. And what we're going to do is we're going to find the electric potential. We use the letter V for electric potential. You'll see why in a minute. So all of this we've been talking about with potential energy. At this point, I'm just trying to motivate the idea of electric potential. In the notes, I literally just defined it this way. Said V is KEQ over R without any explanation as to why. But I want to motivate why we define electric potential this way. And so let's just do that. So one of the advantages of talking about electric fields as opposed to electric forces is if we just have a single charge, let's say we look at some point, P, we can say there's an electric field. So even if this is the only charge around, we can still talk about the electrical properties of it. It is an electric field here. And then if we put a charge there, this electric field is going to exert a force on that charge. Kind of similar thing with electric potential. Let's say that this distance here is R. We can say the potential due to a point charge is given by this equation. So I'm actually going to get rid of potential energy for the moment. Write down this constant. Which I'm blanking on for a moment. Okay. So, sorry, I forgot the units for K. Yeah, that's right. Okay, so this electric or Coulomb's constant, whatever you want to call it, 9 times 10 to the 9th Newton meter squared over Coulomb squared. And we say that for a charge Q, we can say there's an electric potential at this point, a distance R away. So, again, we don't have to talk about, it ultimately came from like an interaction of two charges. We can define the electric potential just due to a charge itself. So it is kind of like that relation between electric fields and electric forces. There's definitely advantages to just talking about properties of individual charges and then treating how they interact with each other separately. And we're going to see later there's actually a very direct and very important relation between electric fields and electric potential. Now this is just one charge. Let's call it Q1. And let's say this point is at a distance R1 from charge Q1. What if we have charge 2 at a distance R2? Then what's the electric potential at this point, P? Well, it's very simple. It's KEQ1 over R1 plus KEQ2 over R2. So again, you just calculate the electric potential due to each of these charges at that point P, and you add them up. And so again, you can easily generalize this to any number of charges. So in theory, if we have this charge distribution, if we have individual charges at definite locations, we can calculate the electric potential anywhere we want. Now, there's a definite advantage to looking at electric potential as opposed to electric fields. So we had something similar. If we look at the electric field at point P, we'd have E1 and E2, and we have linear superposition where we calculate E1 as if Q1 was the only charge that existed. Then we calculate E2 as if charge 2 was the only charge that existed. And then we would add these two vectors to get the actual electric field at point P. Similar with electric potential, except electric potentials are scalars. So much easier to work with than electric fields. Okay, now let's talk about units. I said we'd understand why we use the letter V for electric potential. Let's look at the units here. If we look at the basic SI units, here we'd have K, which is newtons, times meters squared over coulomb squared, times a charge over a distance, so coulomb over a meter. So we'd have newtons times meters over coulombs, or joules over coulombs. And we give this a name, and we call this a volt. So we measure electric potential in volts. And again, that's a very familiar term if even just looking at a battery. You could have like a 9-volt battery or like a 1.5 volt battery. It's a very common term. It's kind of one advantage of the SI system, or a huge disadvantage depending on your perspective. But there's other systems of units that aren't based on volts and things like that. So, but SI really caught on because it uses these familiar terms. Okay, but in some sense, though, SI is very unfortunate. Certain topics as well. But that's electric potential. So in theory, if we have any number of charges and we know where they are, we can calculate the electric potential anywhere, and it is a scalar. So I think we'll look at just one example of that, and then we're going to look at how electric potential is related to electric fields. But I've got an example in the notes, kind of a simple one, but I'm going to write down this conversion factor as well. So, a joule is equal to a coulomb volt. Earlier we had a volt as a joule over a coulomb, but we can just multiply by a coulomb. And again, this is on the equation sheet, this unit conversion factor. But when we look at this problem, we have x and y measured in centimeters. So let's see, we have a charge of 9.5 microcoulombs at the origin, and a negative charge at the location 4 centimeters along the x-axis. And that's minus 5.3 microcoulombs. And we want the electric potential at the point 3,5. So 3,5, let's say that's our point. So that'd be measured, in centimeters. Okay, so let's make some triangles here. So this is at that point 3, so its x-coordinate is 3. Now we have R1 and R2. Now, one thing that's a little bit unfortunate compared to calculating electric fields is we actually have to find R1 and R2. Well, we didn't really have to do that. The way we find them is with the Pythagoras theorem, where we have to like square the sides, add them up, and take the square root. Well, we didn't actually have to do that with electric fields because actually we didn't want R, we wanted R squared, so we never had to bother taking the square root. But let's calculate R1. So again, this side of the triangle, I know this should be vertical, but I didn't draw it perfectly. So this is 3 centimeters. And then it goes up to 5 centimeters. So if we add those up, and then we take the square root, we get the square root of 34. So 5 squared is 25, 3 squared is 9, add them up, 34. So this is around 5.9 centimeters. 6 squared is 36, so we have to be a little bit less than that. See if we need to go any. Okay, 5.83. And while we're here, let's calculate R2. So in this direction, we're going from, let me check, I think, yeah. So Q2, this is at 4 centimeters. So again, this point is at 3 centimeters in the x direction. So this side is just 1 centimeter, that side of the triangle. Like we're going from 3 centimeters to 4 centimeters. And in the y direction, we have the full, 5 centimeters. So if we add this up, we'd have the square root of 26 centimeters, which I'm going to guess is 5.1, but let's check. 5.099, so yeah, 5.1. Okay. So we have both of those distances. Well, unfortunate, we actually have to take the square root, unlike the electric field case, but yeah, now let's calculate the electric potential at point B due to each of those charges individually. So let's just calculate V1. So we have our constant. I would write the formula first and then fill in the numbers, but just because of limited board space. So we have KE, which I'm writing down the numbers. Now the charge is 9.5 microcoulombs, and again, just the same space. Remember, micro is 10 to the minus 6. So we could have 9.5 times 10 to the negative 6, or just have a positive 10 to 6 on the bottom. I prefer that way. And then divided by R1, which is 5.83 centimeters. And there's 100 centimeters in a meter. So let's throw that conversion factor. So let's just look at the units first off. We have newtons times meters squared, which I'm going to write like this, times coulomb. And I'm also going to write this extra conversion factor. A coulomb times a volt is equal to a joule. Or I would write it here, but I don't have room. So a coulomb times a volt is equal to a joule, which is a newton times a meter. So I'm going to put it like this. And then we have coulomb squared and meters. So you can see, everything's going to cancel out. We will get our voltage in volts. So I actually use joule as a newton times a meter. If I had room, I would have written that conversion factor here. But there's our coulomb volt. Here's our newton meter. And everything checks out. So now let's just look at the numbers. we have 9 times 9.5. Well, that's 81 plus 4.5. That's like 85.5 on top. And then times 10 to the 11th. And that's in volts. On the bottom, we have 5.83 times 10 to the 6th power. And so let's just divide this. We'll get 12 or so. We'll get 85.5 divided by 5.83. Oh, I was a bit off. That's 14.7 times 10 to the 5th volts. That's need a bigger board here. Okay. So that's V1. Again, just straightforward, plugging it into the formula. We just want to be careful about units, basically, and of course, just doing the calculations. Okay, now let's look at V2. This procedure is very similar to calculating electric fields, but one little difference here. For V2, let's plug that in. We have 9 times 10 to the 9th Newton meters squared over Coulomb squared. Now the charge, I'm actually going to write down minus 5.3. And again, it's microcoulombs. So again, when talking about electric fields, I said many times, when you plug in the charge, do not include the minus sign. And the reason why is electric fields are vectors, and so I think it's less confusing if you just calculate the magnitude and the direction separately. And so, I kind of emphasize do not include the minus sign there. But since we're dealing with scalars, the potential at this point B due to Q2 is going to be negative. We can put it here or just put it in front because we know it's a negative charge. The potential is going to be negative. All right. And then let's kind of finish this off. We divide by 5.1 centimeters. I'm going to say 100 centimeters in a meter. And then I wrote a little smaller so we can put this conversion factor. A coulomb times a volt is a Newton times a meter. So again, I'll just write it here and then erase it. Let's check the units again. Even though it's literally doing the exact same thing as before. But it's a good habit to get into, just always checking units. So we have Coulomb squared. Oh, I must took that C for, so we have Coulomb squared and then a centimeter. I wrote an extra one here. Okay, start over. Coulomb squared, then a centimeter, and then a meter, and a Newton times a meter. So again, everything cancels out, and we're left with volts. So now what we just have to do is find the number. We're now putting the minus sign up in front. So remember, electric potential, it doesn't have a direction like vectors do, but it does have a positive or a negative. So let's plug in the numbers now. We have 9 times 5.3 divided by 5.1. So those are all the non-10 numbers. 9, 5.3, 5.1. We brought the minus sign out. And then we have 10 to the 9th times 100 is 10 to the 11th divided by 10 to the 6th. So that would be times 10 to the 5th power volts. Okay, so this is going to be a little more than 9. 5.3 over 5.1 is a little more than 1. Let's actually calculate that. Yeah, about 9.35, obviously negative, times 10 to the 5th volts. And again, they have the same exponent. So to find the potential at point P, we would just add these two numbers, or take 14.7, let's say 9.4, just so they have the same. We'll cut off at the same place. So 14.7 minus 9.4, that's 5.3 times 10 to the 5th volts, or 530 kilovolts. Could write it that way as well. Either way. Okay, so again, much easier than working with electric fields because we don't have to worry about direction. All we have to do is worry about a plus or minus sign. And again, it's just arithmetic, so it's not nearly as complicated. But yeah, if you just understand the procedure, here's the formula to calculate potential, and just do that for every charge as if that was the only charge that existed, and then you add up, like here we have V1 and V2. Those are the only charges, so the potential at that point would just be the sum of those two. I'll check and see if I got the same thing. Yeah, 5.32 in the notes times 10 to the 5th. So, always good to double check, make sure you get the right number. But yeah, so basically all we've done here is define electric potential, talk a little bit about like how to calculate it. And the next topic, that'll be a separate video, we're going to talk about the connection between electric potential and electric fields. So that'll be it for this one.